Welcome back to another HVAC Engineering Techie training video. Today's video is on technical commissioning of electrical systems, part 2. Remember, we already did part 1. These were broken in 2 because it's way too long a video. This is Cx-10 in our series. Remember, this is the channel, HVAC Engineering Techie channel, talks all things HVAC and electrical. So this is adding to our electrical system series. So remember, if you already a subscribing member, boy, I really appreciate it. If you're not, if you would consider just becoming one, it's totally painless to you, free, absolutely costs you nothing. No one will ever bug you from it. Just hit the subscribe button down below. Give me a thumbs up if you like the video. It's painless for you, but it's very important to me because Google uses that to evaluate the videos. So I really appreciate you becoming a subscribing member. I really appreciate all of you that are. So let's get started on technical commissioning functional performance test part 2. Thanks. All right, so now let's take a look at the videos that we have available in this training session and why you should look at those. Detailed electrical system design for non-electrical engineers. Electrical engineers should already have all the data. And they might want to look at it anyway if you are, just for a refresher. But if you're a mechanical commissioner or electrical technician, then you should look at this to make sure you understand the basis of design. Not because you're going to check somebody's work doing that, but just so you understand how an engineer actually designs a job. S12, Systems 12, is electric motors and drive systems. Very helpful to understand the drives. S50 is basic electrical. S51 is electrical power distribution. S52 is critical power distribution, which is systems like data centers and operating theaters. S53 is electrical lighting systems. S54 is electrical safety. Cx-9 is the testing of electrical systems, part 1. C10, which is this video, is the technical commissioning of electrical systems, part 2, functional performance test. So these two you need to watch together, obviously, to get the whole story. The reason I broke them apart, they're too long. And you also should look at these S50 through S54. That's important that you understand everything about the commissioning process, and you have the technology. These are all about electrical technology. These are about how to test them. So those will be helpful. Okay, the commissioning process is a pre-design phase, design review, CX testing specification, CX commissioning specifications, observation during construction, installation inspections, testing observations, functional tests, owner training, commissioning reports, warranty commissioning. And these first 2 installation inspections are part of the part 1 video. These are all in part 2 video. There's not a clean disembarkation between these two. It probably doesn't matter if some of these are done here and some of these are done here. It doesn't really matter as long as they get done. This was just a method for me to break the video apart to make them shorter. They got way too long. Pre-functional test. Electrical commission tests are broken down between installation inspection, system startup, and final system functional testing. Now, it's kind of irritating, but when ASHRAE created this term, pre-functional test, they didn't realize that there's actually 2 types of tests in that. One is a pre-startup test, and one is a startup test. Well, I put A and B on them just so we could keep them clear. It's very confusing if you don't understand that there's 2 different types of tests and they put the same name in both of them. An FPT, or functional performance test, or the final system performance documentation of how it's supposed to work and if it is working correctly. Now, mechanical, this is real obvious what these are, and there's a lot of time and effort goes into these. In electrical, these are much simpler, still important, but much less rigorous than mechanical. So power distribution pre-functional test, part B, contractor and tested agent performance test, insulation resistant test, fuse and contact resistant test, polarity tests, overcurrent device pickup and delay tests, ground fault pickup and delay tests, ground fault potential tests, capacitance tests, calibrate and verify the trip settings on circuit breakers by injection testing. And those are as specified, of course. And then we provide a check sheet for each of these. This is just for documentation. It's kind of like if you're supposed to measure a bolt, then a wire, you put that it was done and there was no issue found. switchgear, panels, transformers, generators, ATS, power management equipment, lighting systems, lighting control systems, all electrical equipment, and a check sheet to verify the system startup, document specified tasks, provide actual startup data. So on this one, we're on the previous in part one, we were looking at field inspections. This one, we're looking at what happened when we heated it up. So these have much different data and might have actual voltage in amps and data. So that's why this form is designed to capture that data. Coordination, the contractor quality commit. If he does a good job on this, he's a quality contractor. If he just shucks this off as make work and it's not important, then he'll ignore it and it won't be good. Now, we always ask the contractor, the guy that's doing it, to sign his name on it so we know who done this, so we can hold him accountable for it. And then as a commissioner, we always kind of backtrack and just look at the panels during inspections. Say, well, look, this wasn't done. So then we can back check his check sheet. Pre-functional test. The engineers to perform a special system inspection. This is a code required process, maybe. I mean, most AHJs require this, and what it is, the electrical special system inspections are defined by the local code authority as where and when they are required. Normally they require for main entrance and main switchgear and feeders from the utility transformer. So electrical special system inspection required prior to energizing switchgear. So what the code requires is for the engineer of record to go to the job site and inspect the cables and our bus bar coming from the main transformer, utility transformer, and all the main switchgear that's connected to that. Are they ready to start up? And he verifies that everything's done that he wants to have done before they energize them. And it's just a check to make sure there's nothing wrong. Now that's important to be done, because if you start a system up with a big problem, it's a problem. And I'll give you an example. I had a job where I was starting a large 4160 chiller, and the utility was there helping the contractor energize this building for this large chiller. And the utility guy looked at me and said, "You need to go throw the breaker to energize the system." I said, "Wait a minute, why me?" I said, "I'm just the inspector." Actually, I was the contractor, but I said, "What's the deal?" And they said, "Well, you got to understand, the last building we had 4162, it exploded. And what had happened, and I was the very next building in line, so they had a guy back on the utility pole with a circuit breaker pole ready to pull the circuit breaker in case something happened. What happened, there was a large hotel that started up before me, and a electrician had inadvertently left a wrench across the main bus bars. And what happened is when they energized it, it vaporized the bus bar and took out the substation. So that utility lost the substation because of this problem. And it was because it was high voltage, and it was a problem. So a medium voltage according to the utility, but still. So that can't happen, and you don't want it to happen. What had happened is electrical contractor was taking the lifting eyes off the switchgear, and the guy took it off and laid his wrench down across the bus bars and never retrieved it. And no one ever measured the bus bars after that to notice that they had a direct short. And not only did they have a direct short between two phases, it was a big wrench, and it had all three phases shorted, so it was a problem. Inspection form must be submitted to the local court authority with a PE stamp attached. So they're serious about making sure this is okay. Now, downstream of the switchgear, we can test that later. But upstream, that's important. Engineer, vendor, or testing agent perform load and coordination studies for safety devices in accordance with the code requirements. So normally, a vendor does this coordination study. An engineer can do it. Might do it, but normally it's the vendor or the testing agent can do it, but normally it's a vendor. And the reason the vendors do it is because it's their switchgear, and the engineer has satisfaction with them doing it because they know exactly what each piece of gear is, and there's no doubt, because then he's responsible for it. Pre-functional test, contractor and manufacturer to calculate, program, and set current and fault protection settings per the coordination study. Now, this might be the testing agency or might be the contractor. Now, a lot of times on big jobs, a manufacturer representative will do this for you. The guys who just provide all the main gear. Contractor manufactured program and to verify program of main switchgear data systems per the coordination study. Verify hazard class label is posted on all panels. Very, very important that we know what hazard a panel is. Now, remember, the hazard is determined by what the short circuit capacity of the panel is. If it's 10,000 amps, 20,000 amps, 100,000 amps, that determines what the bracing is in the panel and what the emergency fire would be if there's a arc flash event. So basically, there's from 0 to 4, and 0 just needs a faceplate, and 1 is basically cotton clothing and a faceplate and gloves. 0 is gloves too, and then 3 gets more bigger, and 3 is a big heavy suit. 2 is a suit, 3 is a suit, 4 can't enter it off. You got 4, forget it, you're not going in the panel. You have to de-energize it to enter the panel. Contractor or CA may perform circuit verifications. Now, I'm warning you, you can't do this, but don't. It's a large, expensive task. What this means is that in a design, the engineer may have 10 receptacles attached to one 20-amp breaker, and the contractor installs that. Well, the problem after it's installed, it's very difficult to tell which is connected. The only way to do it is put a tracer signal on the circuit breaker and take a tracer instrument and put it in each receptacle to tell which receptacles are on that breaker. And the reason that's important, if a guy put 15 or 20 receptacles on it, is now not rated for a 20-amp breaker. So those are kind of important to do. There's no really easy way to tell after the fact. So either the contractor has a way of documenting that when he's putting it in, that's fine. You know, if he has a drawing, he marks up red, this is this circuit, this is that circuit, that's fine. But if you ask somebody, have you verified the circuiting, and you get a deer in the headlight, okay, that's a different situation. Field verified lighting circuits are circuited as per the design, including switching, motion sensors, and photocell controls for lighting controls. Power management systems. Now, a power management system is basically a control system for power. So the control system resides in the main switchgear and subsequent panels, and maybe the motor control center, and actually watches all the conditions of the power equipment. And to test this, basically you do what you test a control system. You verify it's communicating, verify point-to-point verification, verify all sensors are calibrated, and then record all the instantaneous readings. So you can go, it's really easy to do. You just go to the power quality and print out the power of all the panels. It'll just give you a report right out. It's pretty easy to do, really handy. Lighting control system, the same thing. This is just a normal control system for lighting. And you do the same thing. The contractor, vendor, or you can do this. Communication verification, point-to-point verification, sensor calibration and testing. You gotta test these lighting sensors if it's got lighting amount sensors, level sensors. Okay, now let's talk about electrical functional tests. Power distribution functional tests. Electrical functional tests may be performed by the CA or the contractor or the testing agency, observed by the CA. Now, I would not, if you're the commissioner, I wouldn't do this unless you've got qualified people on staff that know how to do this and have the equipment. If not, the best scenario is to have a testing agency on the site. You don't control that, right? The engineer specifies it whether they want it or not, because it is a cost. It's more expensive for a testing agency to do this than it is for an electrical contractor. But the quality of work is different also. So they do a thermographic survey test on all power carrying devices, bolted connections, and equipment. Now, these are actually under load, so there has to be a load bank applied here to put these devices under load. Phase balance load survey, are the panels properly balanced? 72-hour power quality survey if specified. May not be specified, but it is. This actually tells you what's going on. Lighting level survey, a critical electrical system functional test. You know, if certain lighting levels were specified, at 50-foot candles, 70-foot candles, you can test that data. Critical electrical system functional tests are a little bit more intensive, and we'll get into that in a minute. Light control system functional tests, power management system functional tests. This happens to be from one of my projects, a third-party electrical testing agency's report. This was a small data center, And you see, he took a thermal image and found a hot strip wire here, and they redid the terminal. This was on a PDU, I think. Retorqued the terminal and got it back into compliance. This says that here. This breaker here was way over temperature, but what this actually was is a temporary breaker they used to connect the load banks. So you have to connect it somehow, so they connect to this breaker, and the breaker's slightly undersized for the load bank. And the testing agency just said, this is not a permanent device, so it's not a problem. They will remove this as soon as the load banks are gone. Same for this breaker. This one, however, this middle leg was way hotter than the two legs, which meant this had a connection problem. So they basically had to re-terminate this cable, re-torque it, and get it back into compliance. Critical system tests. Special electrical function tests may be required for critical systems and are performed by the testing agency or contractor as observed by the CA. Now, critical systems are normally data centers or hospital operating theaters or facilities that require no interruption in power, and they will have two power feeds from different substations so that if anything happens to the utility on one leg, the other leg can pick up the whole load. So the redundant power feeds, and normally critical systems have redundant everything, so they don't have a single point of failure. Load banks are placed on the last panel of the PDU to simulate full load or specified part load. Thermographic survey tests are performed on all power-carrying devices, feeders, bolted connections, and equipment is performed. The first test is normally performed at the beginning at a test at 25% power, and the second test is performed at 100% power. Now, sometimes they do 3, they do 25, 75, and 100 tests, and then they may do a final test after it's been on for an hour. Give it time to burn in. Provide test scripts with actual data for documentation. Then UPSs, which is normally part of a critical system anyway, but it may not be, maybe a standalone. And they're performed by the testing agency or the contractor, observed by you. Load banks are placed again on the PDU or simulated full load or a specified part load. Sometimes on a UPS we'll only use 75% load because they're not actually, their size such that 100% load should never happen or whatever the engineer actually specifies. And these are normally tested on normal power and again on emergency power to make sure they function correctly on both of them. Thermographic survey tests are performed on all power-carrying devices, feeders, bolted connections, and batteries are performed. We need to test the batteries also. The first test is normally performed at the beginning of the test at 25% power, second at 100% power. Again, it may be done in 3 steps. Battery drawdown tests are performed to prove battery bank run times at full or 75% load, depending upon specification. Normally, we'll do a battery drawdown at 75% load, which we think is closer to actual load. And what we're doing there is we just trip the main power going to the system. And since we got a load bank on the devices, we do it until the batteries get to minimum shutdown. And we watch the UPS shut down the batteries when they're low. And we're also testing. We're doing thermographic on the batteries at the same time to see how they're funding during this whole drawdown. Now, when we do that, now we can recalculate how much battery time the system has at full load. And that's important to know that the system will last 30 minutes, 20 minutes, 10 minutes, 5 minutes, whatever it's designed for, and the battery drawdown is done to do that. Thermographic survey tests are performed during battery drawdown test. Best practice is to monitor each battery for conditioning during the test. So if your testing agency has the capability and equipment for this, they actually wire a testing connection to every single battery, and it tests incoming and outgoing power, and it tests the temperature of the battery. So it actually has a temperature probe and has current tracing available and voltage tracing on the battery. So it watches all those parameters, and they bring that data into a temporary SCADA panel and then to a computer so they can data log all that power. And that will actually tell you, if you don't do this, which a lot of people don't have this capability, then basically you're depending on the thermal survey to tell you got a bad battery in the system. So that's kind of a problem. And one reason we don't normally use 100% test, so we don't want to stress the batteries very bad. So we basically use 75% load and run it down to its time. Provide test scripts with actual data for documentation of the test. Here happens to be a hospital. This was a hospital data center. You can see we had a main panel here on the main transformer. That was one test, and then we had another test on the PDUs of the data center. And the reason this gets expensive is not only do you have to rent power sources here, the data banks, but the power banks, but you have to wire them up. So the load banks have to be wired up in cables, and you have to put guards on them so someone doesn't trip over them or that you can drive over them. And so it's pretty intrusive, and it is expensive to set these up. And you want to do all the tests you need on load while you got the data banks present. Power distribution, we've covered this already, kind of. Data transfer, 72-hour power quality. Now, this is for, there's some things here you can't tell any other way but this. And normally I like to see this done after the building is occupied and we're on normal load. It doesn't help a lot to do this if you have the power banks in there, load banks in there. And the reason is because they're not variable. They provide resistive load at a constant set point, so you can't tell variation, which can have a problem with what you want to test. So normally after the building's occupied, we'll run a 72-hour test with a power quality meter, and you put it on the main entrance. You have voltage per phase, current per phase, kW, kilowatt H, maybe kVARs, frequency, power factor, and harmonics. And these are things you can't tell any other way. This you can measure, this you can one-time measure, but you can't test if this bounces around, and you can't test harmonics at all unless you put these power quality meters on it. So all of these things, it's valuable to know this for the quality of the power coming into the project. Provide data log and test comments for the description. So once you get a data log, you can print it out and comment about here's where we see an issue, or if there were no issues or something like that, to have documentation for your power quality test. Power management systems, normally performed by the contractor or vendor and observed by the CA. It can be performed by the commissioner. In conjunction with generator testing, verify that power management control system performs the following. Control system records and tracks the events. Control system energizes panels in correct sequence delay times. Control system records all power system parameters over entire test time. Verify system alarms and events. Verify system reports. Now, provide the test script and test data for documentation. Now, remember that a power monitoring system, power management system, is just basically a control system for power systems. And the one thing it's designed to do, which is especially if you have a bigger job, and I talk about it here when it does system parameters, energize panels in correct sequences for delay times. So what happens is when you have a system on emergency power and the power feed fails, the generator comes up and runs, accepts the load, takes the load, and the ATSs start switching the load. Well, if it's a big job and you have a whole bunch of breakers and loads out there on an ATS, once the ATS switches and they power up, it will start bringing those breakers over in a sequence so they don't load up all at one time, thus causing the generator an issue. So that's what I mean by sequence testing. Now, I've done jobs up to 42 to 45 breakers, big breakers, that have to be energized in a certain sequence, and the only way you can document this is with a power management system. If you got a job that says 2 or 3 breakers, you can stand out there and watch it yourself. But if you don't, you have 45, you can't watch that. That's too many. You gotta have a system to do that. Then once the regular power comes back to life, you have to do that over again. You have to, once power comes in, the ATS to switch back to normal power, then you need to sequence those breakers again so you don't cause utility power. Example, I had a job in Florida. It's a big job. Really big job. Big campus with about 20 buildings on campus, a big building, 300,000 square foot buildings, a lot of them. And we had 2 central plants, 2 generator plants, and I think we were 20,000 amps, 20,000 kW of standby generator at 12,000 volts. So what happened was we had 42 circuit breakers that needed to be scheduled on this. So we went on the generator. Generators came up, accepted the load. Switching happened. The 42 switched. Everything was fine. The power management system got it great. We're in great shape. And then went back to normal power, and the contractor and vendor had not programmed the breaker sequencers back to normal power. When that happened, the generator shut down, ATS switched over, came back to normal power, browned out the utility. It was such a big building, and the utility was kind of on the end of their utility feed, so we had to go in and reprogram them all. So it is a problem. We have to go, the sequence needs to be verified going on and going off both ways. Lighting control systems, basically control system for lighting. In conjunction with the generator testing, verify the emergency lights are on. If there's emergency lights, you want to verify that in the system. Elevators and egress routes mainly. Testing and lighting control sequences. Verify system reports. Now, what sequences might they have? Well, they might have, from a security system, someone cards in at the front door and it turns his lights on in his office. Could be that kind of sequence, or it could be a sequence that at a certain time of day, something happens another time of day, something happens like on and off control, occupancy control, all that stuff. You can verify through lighting control system. Provide test scripts and taste data for documentation. Emergency power functional tests. Generator set. Now, let me back up. The other thing on this test is to verify the motion sensors or vacancy sensors, either one. This becomes difficult because if you have an office area with 30 occupancy sensors, now, of course, the difference between occupancy and vacancy sensor is an occupancy sensor detects when it's occupied, a vacancy sensor detects when it's not occupied. Sounds the same, but it's actually different. So what you have to do is, what you're trying to verify is that the occupancy sensor turns on the lights it's supposed to, and they remain on for a certain length of time they're supposed to. And then when they're supposed to go off, they go off. Well, this becomes problematic if you have 30 or 40 of in a space. So the one thing I always try to do is make sure the contractor has verified they all have the same on time, off time, that they're going to stay on for this long or off for this time. Because if they do them different, it'll drive you absolutely crazy. So then what you can do is come in an evening, go get them all activated, and watch and see what happens on timer. If not, if you're doing it during occupied time, people moving in and out, it becomes almost impossible to test. So this is one that's better to make sure the contractor did it, set them all up the same, so you can test them and know what to expect at the same timing. Emergency power functional test. A generator system, this is exactly what we talked about before. So main power, and verify the following. Generator starts within 3 seconds of the power trip. Generator picks up load and provides normal power conditions. So volts, amps, frequency, and power factor are correct. Emergency power ATS, automatic transfer switches, picks up load within 10 seconds. So if it's an emergency one, that's required 10 seconds. And normally this is emergency lighting loads. That's a code requirement. People can't be in the dark for more than 10 seconds. That's what the code says. Non-emergency power ATSs pick up loads within the specified time. Might be 2 to 5 minutes, or might be longer if you have a bunch of them sequenced in series. So it might be 2 minutes for the first one, 3 minutes for the second. You know what I mean? You could get out maybe 10 minutes or so if they're sequenced. But these are non-critical loads. The verified generator does not stall when large loads are applied. So one of the tests they do is when the generator is running on a normal load, they go to the load bank and pop a bunch more load bank on to see what happens. If it stalls under the load, I don't remember offhand what the conditions are for the loading, but we can do that. It simulates an ATS coming on. Reset main breaker for normal power and verify generator go off. So once it powers back, the generators disconnect. The ATSs disconnect them. Normal power comes back on, and the generator runs in a cool-down mode for a certain amount of time. Verify breaker closing timing as specified sequence. Same thing, so we don't provide voltage droop. Verify the generator cool-down time before it's shutting down. So normally it has a 5-minute cool-down period. Might be longer depending on the generator manufacturer, but you want to verify that. Power distribution functional tests done by the contractor, vendor, and observed by the CA. This is that 72-hour power quality under normal test load, so it has to be done when it's actually in operation. Volts per phase, current per phase, kW, kdBH, frequency, power factor, and harmonics. I forgot to put that on there. Okay, common issues and troubleshooting for electrical systems. What do we normally see in buildings that are issues? So electrical common systems, housekeeping pads. A lot of people ignore housekeeping pad requirements. It is a code requirement, And the code may pick up on it, but normally they do not. Electrical equipment under water lines, that they should pick up on. And if that happens, then the only way to really do that is see if you can talk the AHJ into letting put pans underneath the piping, drain pans that would drain any water leaks away from the switchgear. If they don't do it, then you got to move them. Panel clearances, 36 inches and 42 inches. AHJs normally pay no attention to this unless it's the main switchgear. Where I've seen main switchgear get into problems where they have on the corners, where they have one on one wall and then on the 90-degree wall they have another panel, and they can't share common space. So basically that's a problem. That panel has to be 36 inches downstream from it. Ground risers and cables to make sure they're supported adequately, vertical conduits and cable supports, floor and wall sleeves, flexible conduit lengths and supports, stress conductors due to too short a cable. If you notice in those pictures from the last video, show the long cables protruding out of the back of the panels. They're that way so they make sure they're not too short, that they got plenty of room to terminate those cables properly, because you can't splice a cable. Panel labels are on as per. Most AHJs don't pay attention to the actual panel label. They may punch if it doesn't have its arc flash label. Circuit device location, that you need to look at, because the AHJ won't pay attention to that, only that it's got a list, not that it's correct. Electrical common issues, weather protection of NEMA enclosed rating, to make sure that they have the right NEMA panel if it's exposed to weather. Electrical panel device and mounting brackets and supports. Panel cable management, circuit bracing equipment per plans. Panel circuit cards. Local lug torque settings have been done correctly. And I remember the way they do a lug torque is they take a felt tip and mark across the nut and the bolt, so you can tell it hasn't been moved. And it also tells you it's been tested. Resistive test results, phase rotation, equipment vendor startup and testing, hotspot detection, over 180 degrees. The reason is over 180 degrees can start damaging the insulation on the wire. Unbalanced current load, low voltage, low power factor, high level harmonics, higher low voltage or current peaks. So troubleshooting, what do you do if you got some of these problems? If you got low voltage, it could be wire size, or it could be a high resistive connection. But normally, if you generally have low voltage mini panels, it's that the incoming power is too low voltage. And normally your utility transformers have power taps, so they can change the taps and raise the voltage or lower the voltage. So then you would have to request the power company and raise the voltage. And they'll raise it, 10 volts or so. They can raise it in small, I don't remember what most utility transformer power taps are, but they're a certain increment. They can raise a lower voltage. But that has to be done by the utility. Device trip, low voltage, incorrect settings, wrong size heaters, ground fault, design, load size, excessive resistance, harmonics. If you get trip device, you're going to have to do a little investigation to figure out what's going on. Normally, it's that it's programmed incorrectly. When you get trips, that's normally the case. Low power factor, if you've got high inductive loads in the building and your power factor is too low, the only way you can correct it is the capacitors, unless you have synchronous motors. A synchronous motor can actually be adjusted to affect the power factor. But what causes power factor is induction motors. If you got a whole bunch of them on, you'll get a load. Now also, so a power supply in a computer like a VFD or a computer will actually change and add inductive load. And also LED lights. We used to never worry about lights because they were incandescent or fluorescent. They don't have that. They're resistive loads. But the LEDs do have power supplies in them and can provide that. Harmonics, line reactor is the only way to take harmonics out. Harmonics are all put in by power supplies, which means everything that can cause a low power factor can also cause a harmonic. And the only way to filter it out is put a line reactor that'll filter out that harmonics. But you have to do some investigation to figure that out. Resonance or commutation. This is beyond my pay grade. This happens, the electrical engineer or a special engineer needs to be involved in an engineering study to figure out what's going on with this. Resonance and commutation basically varies the voltage. One varies the current, one varies the voltage, but these are actually, In electronics, they actually design circuits like this on purpose because they can raise the voltage or they can raise the current without reading more power. And you can use resonance or commutation to do that. But in our system, we don't want that. So we want them even. So basically, if that's happening, if you got a high voltage spike somewhere and you can't figure it out, it might be happening kind of resonance. And you'll have to figure that out. Hotspots are normally lug crimp, placement of torque. Wire size or design size is normally a hotspot. Voltage to ground, open neutral. Now, if you have voltage to ground, means you have an open neutral. This is a life safety problem. This voltage to ground should not have any voltage to ground. It's a connection, and it's a pathway, but should not have active voltage going to it. It might have 0.1, 0.5 volts, something like that. It's not important, but if it has real voltage going to ground, there's a problem. Okay, final delivery of electrical commissioning. We have the commissioning report, and it records all commissioning data and communications as an executive summary. And the executive summary basically says, here's the issues we found that have not been corrected, why they haven't been corrected, or when they're going to be corrected, so that the customer knows that these were issues and they do need to be finalized. The commissioning plan that you had, the pre-functional performance test sheet you created, electrical testing reports, functional test sheets and scripts, issue log and observation reports, all correspondence, and that goes into the report. This is pretty easy to do. And then also, if you have a system manual on it, now a system manual is designed to include what an operator needs to operate the systems. We include key as-built. So these key as-built are all the management systems, like power management system, lighting control systems, all the critical power systems, all those systems that need key as-built. For some reason, I don't know why, but some reason as-built never get to operators. Either they aren't created or they don't get there. By putting them in a system manual, you assure that they are going to get there. And the system manual and O&M manuals, the system manual is more important. They actually include the O&M manuals. And the reason is O&M manuals may be generic in nature. What we want is system manual. We want operating information to be unique for this particular device, not open for all kinds of devices. Owner training, we need to perform owner training. Contractor and manufacturers provide specific owner training. Commissioners shall verify and document the training activities. As a commissioner, you don't do training, but you may document it. And the documentation may involve videotaping, and it may involve just verifying schedules. Warranty phase commissioning. If you have in your specification a 10-month or 12-month warranty requirement, the way that's done is pretty simple. You just basically contact the owner and ask what trouble calls he had in the first 12 months of operation. You contact the contractor, the general contractor, and ask him if you could send over a copy of his warranty log. It's no sweat to him. It's already happened. It's good. It gives you a list of everything that happened in the building for the first 12 months. And you review that to see if there's anything that looks suspiciously that may have been a result of something you tested. In other words, you tested it, seemed to be okay, and now there's an issue. You need to follow that backwards and make sure that there's something not still existing in the building that needs to be taken care of. You also then interview the operators and ask, is there any outstanding warranty issues? If there are not, then you're done. You just simply report those two documents, become documents for site warranty visits and review outstanding issues. Warranty issue log, if any, commission report addenda if you need to, because this can happen after 12 months. You've long ago issued a report, issue report addenda. And the last thing is a lesson learned meeting. This is not a requirement by anybody but me. And the reason is this is really important. It's not part of the commissioning process. What you do is you just get a casual meeting with the owner and you ask him, how did the commissioning process go for you? What did it look like? Was it good, bad? Could it be improved? And if he says, this went really well, this didn't go very well, this was kind of rough, and maybe how could we fix that? And you both decide how you could do that. Now, what's very valuable information for you to how to improve your processes and how to improve what actually happens on a job. Now, in a perfect world, we have all these great ideas how this all works, but when you get people involved, things can happen, and it can happen a lot. What you thought was going to work really simple turns into a mess, and that can happen. But what this whole thing is about is actually making sure your customer's happy with you and your process. And basically what you're saying is, thank you very much. Please give me another job, right? You're trying to sell the next one. Because most of the customers you're going to work for are probably people that have lots of buildings. So the lesson learned meeting, I think, is really important. It's fun, number one, because you're getting to talk with somebody about what you did, and they need to just communicate with them. It's really good to do that. They like it, so it's good. All right. Well, I hope you enjoyed that. I hope this was beneficial and you learned something through this process. Electrical commissioning is not difficult, but remember, it's critical and important. And it's easy to document and test. It does take some time. And hopefully this will help you in your career. Thank you very much for watching. I really appreciate it. Remember, if you got any questions, put them down in the comments. I do look at those every couple of weeks, so it's not right away, but I will look at them and answer them for you. And I appreciate you being here. Look forward to seeing you on the next one. Thanks. Have a great day.